All right, so this is actually the 19th session so far. That's the 19th class. So we've actually met consistently for the past 10 weeks, 19 times, and we've done a lot. We've covered a lot, honestly. I was honestly thinking or wondering how we are going to cover most of what we are going to cover in data science. But to be fair, we've actually done justice to most of the things that are important. Right. So the remaining classes will just be some other things that you need to know, right? Just to just cement what you already learned already. And assignment would is going to stop. Yeah. Assignment is going to stop. There will be no assignment for this week, right? So since your project you'll be getting your project this week, I'll let you focus solely on that, and also to revise everything that have been done already. Go through the recordings again. Maybe part of the recordings you need to go through the class materials, do your research, and do a lot of things, right? So I'm just going to give you that time to focus on your project. So there'll be no assignments starting from this week. So this week yeah, you just have to put in that effort, right? To because the project is when you're going to see it, right? Um so yeah, I just wanted to reiterate that so people that missed that would get it. Now for yesterday's variety night, I'm honestly not so impressed with how our turnout is, right? The variety night is actually part of the package for this program. Like it's part of this program itself. So it's not just the class alone. So these are the things. There are a lot of things. People that have consistently gone for the variety night would come out with extra knowledge than you that just attend classes, right? Because there's some things that as a tech person, right, as a data scientist, you don't work in isolation. You don't work in isolation. Joshua, you are unaware. Is it about the variety nights or what exactly? So you don't work in isolation as a data scientist or whosoever it is you are, right, in a tech space. You interact with people, and to have this skill, interpersonal skill, and workplace skill, there are some things you need to know, right? There are some things you need to know, and these are the things that are discussed in the variety night. I posted the variety night yesterday. The announce on the announcement group chat. So you can't really say you weren't aware. Probably you didn't go through the messages. And I think I've said it here before, right? I've told us about the variety night and just encouraged us to just take out our time to attend it. So we're already wrapping up basically. So the ones that are remaining, please try as much as you can to attend it. It's not good that everything would have to be because of mark, like you want to get mark. I believe I just think that I believe that if there was no mark attached to the attendance, some of us might might not even be here. We'll just wait for the recording to drop and they'll go over it. So, but please just try to like get everything you can from this program. Right. There are still other packages that are waiting us, as I've said before. Right, you love enjoy, and so you're part of those people. Well done. So there are still other packages that are still ahead of us. So it's not we're not done yet. We're actually not done yet. So don't see it as we still actually have a lot of things to do. So just still put on your put do the best you can basically, right? And as you all know, the bank promised you something at the inception or the beginning of the program, right? That they will be taking in some of the best students from each track, right? And other companies as well. So you see, there are a lot of things. There's a lot of things like to get from this program. So if you've not really been doing your best or putting in your best, then um it's not too late. You can still do so. You can still do so. Although it would have been better if started earlier. Right. So I'm just trying to encourage us just because we are gradually coming to the end of the program. Right. Actually, it has actually been a ride. Okay, this is not the last class, so let me not go that go down that path. So yeah, so we actually have something for today. So yeah, we have something for today. As I said before, that is our normal class. As I said before, we are going to have a special class probably at the end of the program where everybody will be given opportunity to talk. Right? We'll literally use the like 1 hour or so to just talk and express ourselves, talk about our experience so far, how the program was, and what you've gotten from it, and what have you, right? So we're going to do that towards the end of the program. So just prepare yourself, right? I believe a lot of us here have actually gotten a lot aside the technical aspect, right? The stuff we've been talking and we've been teaching you over the weeks, right? So there are a lot of things that you've gotten from the program. So I would actually love to hear all of them. I'd love to know how far you've come, right? So when that time comes, you get the info. So but for now, just prepare ahead. What you have ahead of you now is to wrap up or finish up with the curriculum. So we're actually almost done. So we've covered fairly everything we need to cover. All right. So and as I said before, your project you get it after the Sunday class. Yeah, probably Monday or Tuesday. So you start working on it as soon as possible. Right. So yeah, it's going to actually be a whole lot. Like it's going to be an experience basically. So the project, you are free to ask questions, make your research. I just need you to be able to work on something, right? To gain that experience. Right. So the things we've been doing so far, I've been giving you assignment. We've actually been doing a lot in terms of the assignment. So those are just like snippets, just portions and part of a whole. So the project is going to kind of take you from end to end, from beginning to end, right? So you're actually going to walk through that process yourself. So it's going to be very intensive, and I I believe you enjoy it. I believe you enjoy it. So so yeah, let's just go to what we have for today. Right. So last week, I'm going to be sharing my screen now. All right. So please, can you confirm if you can see my screen? Let me know in the group chat if everyone can see my screen. All right. All right. Perfect. So yeah, thank you very much. So we are going to be looking at what we call ensemble learning today. Right, we're going to be looking at ensemble learning. This might actually sound new to a lot of us, right? But most of what we've been doing so far actually new concepts. Actually new concepts. So I believe we've actually gotten a hang of what we've done so far. So I've introduced machine learning to us already, so we've gotten comfortable. So I want to believe that everybody here have gotten comfortable with the introductory aspect of machine learning. Please, can I get feedback in the group chat? Right now, you can actually comfortably view the model and evaluate the model and do stuff on it, like the basic stuff that we've done so far. I hope everyone can do that comfortably without much pause or supervision. All right, exactly. So that is actually the essence of the assignment. right? The assignment we've been giving you is just to help you to practice, right? You don't want to leave the practice to just you yourself, right? So we want to motivate you, we want to like push you to go beyond what we've learned in the class, right? So if you've been keeping up with the assignment so far, trust me, you are very good to go. You are very, very good to go. So um yeah. So last class I'm just going to briefly recap on what we did last class. So in the last class we looked at okay, let me just ask you, what did we do in the last class? Let me know. What did we look at in the last class? Okay. I'm waiting for us to respond. What did we do in the last class? All right. Said KNN, SVM, decision tree. Yeah. So basically, we looked at some algorithms, right? We looked at few machine learning algorithms last week, and we also implemented them. So just give me a minute. Let me see if I can open the material here. Exactly. Evaluations, algorithms, CGA, KNN, SVM, session tree, implementation. Right. So can someone just mention all the machine learning algorithms we've done so far? I just list them in the group chat. Everything we've done so far. And when you're telling me KNN, I don't don't tell me KNN. Tell me the full meaning. Write out the full meaning, right? So you need to get comfortable with the lingo, right? So once you are comfortable with it, you can now start using those abbreviations or acronym. So can someone list out all the machine learning algorithms we've learned so far? Linear regression, logistic regression. Exactly. So, see, I need us to respond. Like, I don't want just select few persons. I need everybody to actively participate. This is the class, right? If you are in a physical class, you definitely participate. So just assume you're in a physical class now, right? So, it's going to help you. It's not me, right? It's going to help you to learn better and to have a good experience. So if you know the answers to the question, to be nice if you drop it in the group chat. All right. The other time when after the class, I asked us to drop what you've learned, right? So I know why I do that. I know why I do that. I want you to think. I want you to actually reflect on the class that we've done and pick out those things that you were able to learn from the class. Even if you notice in the assignment I give, not just this one, I think in some of the assignment I've given, I usually include that. What exactly did you learn in the last class, right? So you understand that we are trying to help you learn effectively here. So, all right. So, linear regression, logistic regression, k nearest neighbors, decision trees, random forest, support vector machine. So, before I'll just do a quick revision, like asking us questions, random questions on these ML algorithms, all right, before we move on to what we have for today. So, out of all these algorithms, right? Which one um which one uses a hyperplane to divide between classes? Which one uses hyperplane or a plane or a line, what anything you want to call it, or a decision boundary to divide between classes? Okay. SVC, SV, SVM, SVM, SVM. All right. Logistic regression. Nope, nope, nope. It isn't. Support. Okay. So I'm waiting for a few more responses from us. SVM, exactly SVM. All right, SVM. So that's nice. I want to believe that you are not just putting SVM there because every other person is putting SVM. Right. So if that is not the case, then I'm happy that we still remember that. So now, second question. Which of the algorithms, right? Which of the algorithms have a parameter called max depth? Max depth. Which of the algorithm has a parameter called max depth? Wow, that's fast. Nice. Okay, decision tree. Hmm. Let me see more answers. It might not be correct. Oh, decision tree. Okay, that's nice to see. All right, so okay. That's fine. All right, so what is the name of the parameter you use when initializing KNN? There's a particular parameter you use or you include in KNN. What is the name? What is the name of that parameter in sklearn? When you are creating your KNN object, right? What is the name of the parameter that is you put or you include in the class? Hmm. Who is this person? Shamuno Dahiru Aruna. Like, I'm actually very impressed with how fast you answer these questions. Yeah, yeah, exactly. N neighbors. No. OAMA. That's not it. It's N neighbors actually. Yeah, you're correct. You're correct. So that's nice. That is nice to see. So don't feel anyhow. Like this is just been interacting. We are just interacting here. Like you can get it fine. If you feel it fine, we are just interacting. At least you learn from this, right? And then improve yourself as we are moving forward. All right. So let me still go on. Um, what is that function? The name of the function that takes in a value, a continuous value, a continuous or integer value and squeezes it or puts it within the range of 0 and 1. So the particular function in and in which algorithm is it used in? Which algorithm is it used in? ROCAUC, sigmoid function, logistics, sigmoid curve, sigmoid, min max scalar, logistic regression, standard scalar. Okay. All right. So now I understand why some of us are putting min max scalar here and standard scalar, right? So standard scalar and min max scalar, the realization techniques, right? They actually um they reduce the value of variables to a specific range, right? But that's actually not the answer. Um, Standard scalar reduces it to between -1 and +1. Just the mean just have to be 0. While standard mean mass scalar is usually between 0 and 1, where you can make it between any number basically. But what I'm asking about is the sigmoid function actually, right? So the sigmoid function is the function, right? I said which function, right? So the sigmoid function is the particular function that takes a value, right, and puts it between 0 and 1. So these are some of the things, simple things or casual basic thing you need to know, right? If you go for an interview now as a data scientist, these are the things they will ask you. Just basic question, right? They might not really go in depth like that until maybe there's a technical aspect. But these are the things that you need to know as a data scientist, right? So I'm just trying to assess our knowledge. I'm just trying to just take a few more questions before we continue. So okay, okay, let me see. Okay, what is the name of the module? The name of the module in where we import um decision tree models from. What is the name of the module we import decision tree models from? I hope you understand what the module is. I think I've explained that before. So what's the name of the module where we import decision tree models from? Tree. Exactly. 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 Okay, so I think I'll just stop here. I'll just stop here. So hope you um I believe we really enjoyed it. So we're just going to continue with what we have for today because of time. So I'm impressed honestly, right? We are actually still familiar with most of the things we've done, right? So that's actually nice. Okay, let me just ask last question. List or name four pre-processing techniques in SQL, in sklearn rather. Four pre-processing techniques in sklearn. Four pre-processing techniques in sklearn. I'm waiting. Pre-processing techniques in sklearn. Just four of them. I believe we did that in the introductory introduction to sklearn. Yeah, we did that. So four pre-processing techniques. Mm-hmm. Mm-hmm. Then drop NA, fill NA. Um, okay. Drop NA and fill NA. You can just put them under the same um technique. That is handling missing values. Just handling missing values, basically, right? So. Okay, I'm seeing some things here. Normalization, imputer, simple imputer, exactly. Label encoder, one hot encoder, standard scalar, um, data transformation. Okay, data transformation is actually vague, right? The data transformation encompasses a lot of stuff, so you have to be specific with the kind of transformation you are doing on your data, right? So standard scalar, standardization, data cleaning. Yeah, still the same thing. Data cleaning is a broad term. So you have to specify what part of the data cleaning or the type of cleaning you are doing on your data. So so yeah, we can actually go on and on and on and on and on, right? But I'm just going to stop here. So I believe this is just to just um assess our how far we've gone with what we've been doing so far. So I think we are actually good. So just keep on revising, keep on going back to what we've done. Try to, if you probably missed some things in the class, try to go back to the class recording and just take your time to understand it. And I want to believe at this point that everybody has actually been practicing aside the assignment, right? Aside the assignment, I want to believe everybody has been practicing on their own, exploring, or it's not everything we are doing in this class, right? So there are a lot of other things that you can do, right? And I see it in your assignment and I'm impressed. When I see some things that we didn't do in class, I was like, yes, this person has gone further to do research, their own personal research, which is very, very wonderful. So I want to believe that everybody has been doing that because our project is not solely going to be on what is not going to be strictly what we've done. Like, so you're going to have to be creative. You're going to be, it's going to also test your ability to research and to read up documentations, to go to SKLN website, to go to this place. It's just going to assess your ability to do all these things. So it's not just going to be garbage in, garbage out. Like it's everything we've done in class. No, 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 it's not going to be like that. That is not how the world works, right? So I'm going to try as much as I can to tailor the project, right? So you would actually learn a lot from it. So yeah, that's it. That's it. Let's just go to what we have for today. All right. So we've basically just as done the revision, right? We've done the revision of what we did in the last class. Done the revision of what we did in the last class. So I'm just going to go straight to what we have for today, right? So today we are going to be looking at um ensemble learning, right? I'm going to be looking at ensemble learning. So this is this is a new concept, so please just pay attention. This is a conceptual or theoretical. Mostly, it's going to mostly be a theoretical class. Although we're going to do some implementation in SQL just to show you one or two things, but it's mostly going to be a theoretical class trying to help you understand some of the algorithms, right, under this group of algorithms. So we're going to basically help you to understand this group of algorithms that we're going to be looking at today. So what is ensemble learning? So before now, if you are familiar with the word ensemble, you know that ensemble basically mean what, right? Can someone tell me what exactly does ensemble mean? Right? In the normal layman English term, what does ensemble mean? What do you think, or what do you think it means? Okay. Group, gather, put things together, exactly, combination. So exactly. So that's that you are perfectly correct. So that is what ensemble. Ensemble is when you gather something together, bringing a collection, a group of things together. That's what ensemble mean. Right. So now in machine learning, we have what we call ensemble techniques. That ensemble techniques, right? These are algorithms that we can also use in creating or building models. So we're going to look at them today. Right. So for your assignment, the correction is going to be done tomorrow. Right. It's going to be done tomorrow. So in case you are thinking about that, and hopefully you get your grades tomorrow or by latest Monday. So we are not going to be having any assignment, as I said, for this week. I'm just going to be giving us resources and some things, some tasks to complete and some things to do, just to keep you busy as you're working and focusing on your project. So ensemble learning here refers to a machine learning approach, right, where several models are trained. Remember before we've been talking about decision tree, logistic regression, linear regression, k-nearest neighbor, what have you, right? But in this particular type of machine learning, you don't just train one model. You train plenty models, plenty of them, right? And then use their combined power to make predictions. Like you basically group them into one model. You train multiple models and use their collective predicting power to make your predictions. So from the explanation alone, you know that oh, this is actually going to be a very good model because two heads are what better than one. So sometimes our model might be prone to make mistakes, right? So when you have like let's say five models that you've trained, let's say out of that five, two of them made mistake, right? They're not really correct, and the remaining three are correct. So once you use the combined power of that five models, that ensemble technique, you're going to actually get a very good prediction because you are getting a majority vote that is correct. So you're basically trying to utilize the power of number in this instance. Do you understand? So we're going to look at them. We're going to look at the examples. We're going to look at the approaches. We're going to look at the methods, and we're going to look at how we can just implement it simply in sklearn, right? So this example, it refers to a machine learning approach where several models are trained to address a common problem, right? And their predictions are combined to enhance the overall performance. You can see it here. So in this case, you're not just relying on one single model to make a prediction. You're actually using multiple models, like one prediction, right? So as we are going, we're going to be talking more about that, right? So the idea behind ensemble learning is that by combining multiple models, each with its strength and weakness, the ensemble can actually achieve better results than any single model alone. So this main idea, the core idea behind ensemble learning, this is the core idea behind it. Each with its strengths and weaknesses, the ensemble, that is collection of models, right, can achieve a better result than any single model alone, right? So basically we are going to be looking at the types and everything. So this is just basically saying the same thing. So now in ensemble learning, it is basically categorized, right? We're going to be looking at a lot of types, categories, and a lot of things. Just try to pay attention to all those things, right? And now generally we can classify ensemble methods or ensemble algorithms into two types. The first one is parallel ensemble methods, right? Second one is sequential ensemble methods. So this will actually be overlapping with some of the things we are still going to talk about later on when we talk about bagging and boosting. And remember, I sent us a video on the Google Classroom, about 3 videos to watch. How many of us saw those videos? Please let me know in the group chat. How many of us actually went through those videos and picked something from it? I didn't just put that there because I felt like putting something on the Google Classroom. I needed us to go through those videos. So although no mark was not attached to it, but all right, okay, that's actually nice to hear. So if you remember in the video, I basically there's some things that were in the video that we're not going to talk about today. They talked about normalization, the difference between normalization and standardization, right? So that's another concept for another day. We've discussed that, and they also talked about random forest algorithm. So now this is one of the things we're going to be looking at, the random forest. So as we are moving on, and as you've watched that video, you've seen that video, it will make more sense to you as we are discussing some of the concepts today. So as I said, ensemble technique is grouped into two: parallel ensemble and sequential. In parallel, the models are trained independently and their predictions are now combined, right? So basically in ensemble, you train several models, you just train them. There's no connection between the models, right? So they are trained independently, right? But the way it is done for you. You don't need to do them by yourself. There are and things that you can call in sklearn to do those things for you. But just know that the way it works is that in the algorithm that uses parallel method, the models are trained independently, and after they are trained, then each model cannot be used in making its own independent decision or prediction. So once it has made its prediction, you will now gather the predictions of all the models, and depending on the kind of task you are doing, you can use voting to get the, because you need to get one prediction. That if you want to make a prediction, it's just one value that you need. It's not, you don't need five values or 10 values. You need one value. So once you train, like, let's say 50 models, like, and in using ensemble technique, right? And let's say in this case, parallel ensemble methods, you can basically train all of them, and then each of them can make its own single prediction, and you cannot get the predictions from all the 50 algorithms models. So what you have now is 50 predictions. So the way you can now decide on the final prediction is what we're going to be talking about next, right? So it depends on the kind of task you're doing. If you are doing a classification task, then you are going to use a different method to pick the final prediction. If you are doing a regression task, you're going to use a different method to also pick the final prediction, right? That's for parallel. Now, for sequential method. So sequential method is kind of different. So sequential methods are actually trained sequentially. So there's a connection between each model, right? One model will be trained, right? Once it is trained, it will now, the second model or the model that is following it will now use the information, or it is now going to try to improve on the model that has been trained already. Like, it will look at the mistakes that the model before it made and now try to correct those mistakes, right? So it does it sequentially. So there are algorithms that do this thing for you. So you kind of, that's why we'll talk about it later, right? I don't want to just explain everything now. So these are the two different methods in ensemble. In parallel, they are trained independently. In sequential, there's a connection. So the first model is connected to second model is connected to third model. So basically, although all of them are trained independently, but all the models will still have to make their own single prediction, right? And the final prediction will now be chosen based on a certain criteria. So that's it for ensemble learning. So I believe this has introduced you to the concept, right? So let me just go over it again. Ensemble learning is like collection of models. Instead of using just one model to make or to make prediction, instead of building just one model, you can actually build multiple models. Why do one when I can do 100? So that's actually the question. Yeah, why do one like when I can do like 100? Why build one model when I can build like 100 models, right? Two heads is what better than one, even better. 100 heads are better than what? One. Right, so that is just the idea that will keep ringing, or that will keep going over, will keep going over in this particular ensemble learning, basically. So now I was talking about something that once the models in the ensemble learning has made its prediction, like let's say you have 50 models and 50 of them made their single prediction, that is 50 predictions. How are we now going to determine the final prediction? That's what we're going to be talking about now. So there are two ways. The first one is what? Max voting. And the second one is, okay, so there are three ways actually. The second one is averaging. And the third one is weighted averaging. Weighted averaging, and max voting. So these three techniques for selecting or for getting the final value, right, depends on the kind of task you're doing. Right? If you are doing a classification task, you use a different selection technique. If you are doing a regression task, then you use a different one, right? So now for max voting basically is, as you can see here, is an ensemble technique used primarily for classification task. You understand now? So when the task you're doing is a classification task, like I think the diabetes data set, the classification data set, right? So in such a situation, you build a model, right? You build an ensemble model, right? A collection of models, basically, like let's say 50 of them, and each of them was trained on the data. So once we'll go into the nitty gritties as we are moving forward, but just get this the core idea here. So each of them is they are trained on the data set, right? So after they are trained, then they'll make a prediction. After they are trained, they make a prediction. After they're trained, they make a prediction. After they're trained, they make a prediction. So they're basically just exploiting the different strengths of the different models that we have in here. Although the models are not the same thing, we'll come to that later. Right. So once you've done that, you now have 50 predictions. So let's say 40 of them predicted um your value to belong to class one, and the remaining 10 predicted it to belong to class zero. Looking at this, which one are you going to decide on, or which class are you going to go with that? Okay, this is actually the actual class of my data that you've passed in. So if you have this particular output now, which one are you going to go? Are you going to go for class one or class zero? Based on what I just said now, let's say you are the one selecting at this point. Exactly. So it's just a very intuitive stuff. It's just like coming to a particular, you have a group of students, right? Like you have a group of students, or you have a group of people, let's just make it generic, group of people, like let's say 70 of them, and you wanted to know something, right? You wanted to know something, or you ask them a question, you don't really know the answer to the question, right? So you ask them a question that can either be this or that, right? And you now ask each of them, each of the 100, let's say 100 student persons, each of the 100 persons, you ask each of them that question. So out of all the 100 students, 80 of them told you that the answer is A, you understand? And then the remaining 20 of them told you that the answer is B. So based on majority votes, you are going to go with what? A. That is the idea behind the ensemble, basically, right? In terms of classification technique. So you're going to go with A because you know that there is no way that all these 80 people will know they will not know anything. Like the error is so minimal, right? Like the chance of them being wrong is so low. You understand? So that's why we use voting in selecting and doing anything we are doing. Let's say you want to make a decision and you, in a company you vote. So you know the majority are always almost always right, basically. So that's the idea here. So we have max voting, which I just explained now. Right. So max voting is an ensemble technique used primarily for classification task. Understand? So in this method, multiple models are trained independently, and each model casts a vote for each class. Now, the final prediction for a given instance is determined by the class that receives the highest number of votes from all models. So I believe this is very clear. This is very clear. So this is basically the first way to get your final prediction from all those models that you've trained, right? So basically, these are the key points to know about this particular voting method. It's simple and intuitive, right? So it's normal human stuff. So you don't need to, there's no mathematical stuff that you need to know. It's just straightforward, right? So model diversity. So this actually helps it benefits from diversity of individual models, right? So you get inputs from different models. So it is robust too, right? It reduces the impact of any single poorly performing model. So let's say out of your 50 model that you created, five of them are actually very bad. They don't predict very well. So if you get majority vote, there's a chance that the five that are bad will actually not contribute significantly to the vote. So that is another advantage of that. So and also the applicability, as I've said, it is best suited for classification problems, right? It is best suited for classification problems. So we're going to go to the next one that we have here. So the next one we have is averaging. So as I said, the technique here depends on the particular ML task you're doing. So averaging is as mass voting is for classification, averaging is for what? Regression task. Understand? So in this case, let's say you trained an ensemble of models, right? And each of those models are actually trained on a classification task, right? So they'll have to make a prediction that is what a numerical in nature. So to pick or to get the final prediction, what you just have to do is just to get the average of all the model predictions. So you have to add all the predictions together and divide it by the total number of models you have, and you get an output. So that is going to be your final prediction, right? So these are just very straightforward stuff. Nothing technical about it. So let me just read through it. Averaging is an ensemble technique used primarily for regression tasks, right? So although it can be adapted for classification, but basically this is just what is it is used for. It is used for regression tasks, right? So um, the final prediction is obtained by calculating the average of predictions from all models. You understand? So these are the points to know. So basically, we'll just move straight to the next one because of time. So the next one is weighted averaging. So this is the same thing as averaging, right? But the difference is that each model does not contribute at the same level, or they don't their contribution is not the same. So some of them, their contribution is their input is taking is more valid, right, than other models, right? So basically, what happens here is that we have like 50 models in our ensemble models, right? And each of them are actually given weights. The weight is going to indicate how how much what's the word? How much power that model will have in predicting or in making predictions. So basically, in the ones we've done already, each the averaging and the max vote, all models in this case, they have equal power or equal they have equal rights in contributing to the final output. Yeah, that is it. So they contribute equally to the final output. But in this weighted averaging, the models don't contribute equally to the final output. Right. So depending on how good that model is, that model might contribute more or less. So if the model is not really good, it's going to contribute less. If the model is good, it's going to contribute more. So there's a way the weights are assigned to each model. So the weight will be multiplied by the prediction, and you basically it's just basically going to affect the output. So this is just the third way to get the final output. So that is just it for that. So we have max voting, we have averaging, we have weighted averaging. All right. So as you can see here, weighted averaging is a more sophisticated version of averaging technique, right? In this method, different weights are assigned to the predictions of each model based on their performance. So if the model is good, a bigger weight, a weight in this case is just a number. So a bigger weight will be given to that model, which will be multiplied with the prediction. So if a smaller weight, let's say 0.00 something, is multiplied to something, what is going to happen? It's going to reduce it. You understand? But if a bigger number is assigned, let's say 2 or 1 point something, it's going to increase the value, the initial value. So that is just what happens in this particular instance, right? So the key points to note here is that weights are typically determined by performance of each model. Understand? So with better performing models, better performing models will receive higher or bigger weights than poor performing models. So basically, it's also flexible. This technique allows for flexibility in emphasizing more reliable models while still incorporating insights from other models. It's just like in a class now, right? You are a teacher. You know people that are top performers in your class, like people that you've been teaching for a long time. You know people that are always doing well and their grades are very good. So when you want to you want to get input from the entire class, you're actually going to pay more attention to those particular set of people. That is what giving weight mean now. So you are giving more weight to their opinion, right? So they are focusing on their opinion or their input will have more impact, right, on the final output or the final value. So those people that are just there, that they don't really attend class, they don't really they're not so serious like the other people. Their opinion will be taken, right, but it will not be considered that much like people that are very serious and are just there, right? So that is just the idea behind that. So it improves accuracy. So weighted averaging can actually improve the accuracy of ensemble by giving more importance to more accurate models, right? So complexity to actually is more complex than the other one, right? The other ones are just averaging and mass voting, but in this case, we are actually going to be doing there's going to be an extra step, right? So we would have to determine the appropriate weight that will be given to each model. So it can actually be complex and may require validation techniques. So, but don't worry yourself. All these things you're not going to do them. Like it's not in your place to do all these things, right? This is just concept. We have to understand the concept. So when you're implementing it, you understand what is happening behind the hood. As you've seen before, training a model is just straightforward, model.fit. But what happens when you do that model.fit is what you should know as a data scientist. So it will help you to tune your model to be able to make your model better. Right? Tomorrow we're going to be actually looking at hyperparameter tuning, which is actually one of the most important aspects of machine learning, like very, very important. So just keep that at the back of your mind. So basically, this is just a summary of everything here. So max voting is best used for classification problems where a consensus decision among models is desirable, right? So it leverages majority opinion and works well where there is significant. So basically, this is just a summary of everything, right? Basically, they are quite different and they have their own use cases. So we're going to be going to what we have next. We've introduced ensemble tools. We talked about the two general methods, that is the parallel ensemble method, which you train each model individually. There's no connection between them. We have the sequential where there's actually a connection between the model. The next model would learn from the mistakes or the error of the previous model and improve on it. So um there's an improvement as you are moving forward. You understand? So actually an improvement. So the sequential is always more efficient and actually better than the normal parallel. So now we're going to be looking at two core techniques in ensemble learning. So this is supposed to be bootstrap aggregation. Okay, so now we're going to look at bagging and boosting. So bagging and let's see the other one, and boosting, right? So we're going to be looking at those two things. So the two most important concepts in ensemble learning. So what's bagging? Bagging is actually a compressed form or a short form for bootstrap aggregation. So just so you know, this is not an algorithm. This is not an algorithm. We have algorithms that are under bagging. This is actually a method, right? So we have algorithms that uses this bagging technique or method, and we have algorithms that uses this boosting technique and method. So just keep that at the back of your mind in case you already concluding that this is another algorithm. No, bagging is not an algorithm. Right. So it is a method in machine learning where we use multiple versions of a model to improve its performance. So it's the same thing. It's actually almost the same thing with that parallel ensemble learning, right? So in bagging, let me just finish this. So imagine for now you want to get opinion um, from experts, right? Okay, I'm going to give you an example later. But basically, it is a method where we use multiple versions of a model to improve its performance. So we have a data set, right? And what do you do when you want to train a model? You split your data set and you train it on a model, whether you use decision tree and whatever, logistic regression or KNN or SVC. So you train your model and you get a model. You train your algorithm on your data to build a model. And when you get your model, you can now use your model to make predictions, right? So in bagging now, bagging, you actually do something different, right? You randomly select portions of your data set. Let me explain now. Let me give you an example. Let's say you have a bag, right? You have a sack. Now, in that sack, there that sack is actually your data set. Just imagine that's your data set. So you have like 100 balls, or let's say 200 balls, right? So each of these balls, they're actually unique. So they are they're unique. You can actually distinguish them. Probably they have an ID written on top of them. So in bagging, what you do is that you select randomly, or you create different random samples from your data set. Let me go again. In bagging, you create several random samples of your data set. So if you have a data set right now, let's still continue with that bag. You have a bag of 200 balls. Now you can, from that bag, now create like um let's say 5 different bags, right? So you can now select randomly from that your original bag and now put or create new bags based on what you already have, and you do it randomly. So in this case, you just have to find extra bags, just put them on the floor, wherever, and then you close your eye because it's a random process. You put your hand inside the bag, take one ball, put it in one bag, right? You understand? But there's a step now that makes this different. It does sampling with replacement. So once you bring out one ball from that bag and put it in another bag, you can now it's actually practical. It's practically not possible to do it, sure, but basically that is what happens when the algorithm is working. What happens is that you now carry that same ball and still put inside the original bag, but you already put the new ball in that bag. So you imagine that that new ball or that ball is randomly selected is already part of that new bag, right? So you just write it out or something. You write it out, bag one, you write the ID, right? You close your eye again, you shake it, you then trick your hand, bring out another ball, right? And then you would put it in bag two. So you write the ID there. So you do that for the 5 different bags. Understand? Or the 5 different bags. And you can select, like, let's say, out of the 100 200 data sets you have, you can just select random, let's say 80 or 70 or what have you. So the algorithm is going to do all these things for you. But basically, it samples from your data set different samples randomly. And those different samples is actually what your model would now be trained on. You understand? Because you check it, if you want to create an ensemble learning now and you are training a model on the same data set, it's going to constantly give you the same thing or almost give you the same thing. You understand? And in ensemble learning, you use just one algorithm. You don't use logistic regression. You now use decision tree. You don't do it like that. You use just one single algorithm. And in this case, in ensemble learning, it is called estimator. It's called an estimator. So you use one type of estimator. If you want to use decision tree, you use only decision tree, right? So that decision tree, what differentiates the different model is actually the data set. The data set that is being used to train those models in your ensemble model. are actually different. So your model or your data, your algorithm is being trained on different data sets, right? So if it's making prediction, it's making predictions based on what it has seen. So these are just what makes this ensemble learning actually very, very efficient and better than just training on one single one. So let's just move on to see how bagging works, right? So this is actually a very conceptual class. So just follow me here. We are actually still going to do some coding, right? But I need you to understand some of these things. You understand? So one thing you need to know about machine learning or data science is that data science is not like programming. Like it's not like software development that you just enter your laptop, open VS Code, start coding. You just start coding. No, data science is actually a scientific endeavor. That's why they call it data science, right? So it is based on some theories, it's based on concept that you need to understand before you now start implementing. So there are a lot of things you need to know. There are a lot of concepts, a lot of theories, right? Although you don't need to overload yourself with information, but just learn the things that are necessary for you to implement, to be able to understand the implementation. That is what makes you or distinguishes you. You understand? So let's just move on. Because normally in software development, they don't do types of this one, types of that one, types. No, you just go straight to VS Code. Oh yeah, create this function, do this one, do this one. It's purely coding. But data science is not purely coding. You have to. There are a lot of things like you have to know, right? I'm not saying that there are not things that's some things that are not things that you need to know in software development, but compared to data science, you actually need to be grounded in a lot of concept. Understand? So, how does bagging work? So, first thing here is bootstrap sampling. This is actually what I just explained now. Bootstrap sampling. So what happens here is that in this stage, the algorithm creates several new data sets from the original one by randomly picking samples with replacement. What is replacement? This replacement is actually very important. You understand? So replacement in this case is that if you pick, let's say you have um 10 numbers now, right? You have 10 balls that are labeled 1 to 10 inside a bag. What replacement means is that when you pick one, let's say you dip your hand inside the bag and you randomly pick one ball, and that ball number is what? 6. You've picked it, right? And now you can now write it out somewhere. Okay, this one belongs to group one. Let's say you want to separate them into two groups, right? You say this particular number belongs to group one. Now, replacement means that you now have to carry that ball and still put it back into that bag and shake it again and still dip your hand and pick. So there's a possibility that you even pick that ball again. You understand? That's what sampling with replacement means. Sampling without replacement is when you put your hand, pick that ball, throw it away. It will remain just 9 balls. Pick again, pick another ball, put it in a group and throw it away. You have 8 balls. So that is sampling without replacement. But sampling with replacement, you have to replace that thing that you are sampling. So that is what this bootstrap bagging, this particular case of bagging does, right? It randomly picks sample with replacement. You understand? So this means that some samples may be picked more than once, and some may not be picked at all. You understand? It's a random process, so you can't really control what happens. So each new data set is called what? Bootstrap sample. Another thing you need to know. Whenever you hear bootstrap sample in Ensemble, you already know what it means, right? It is the data set that was sampled randomly from your original data set. You understand? So once this is done, understand, the next thing that will be that the next step is to train a separate model on each bootstrap sample. So that is when the training multiple model comes in. So depending on the number of bootstrap sample you have, you're going to have the same number of model, right? That will be trained on them. You understand? So now these models are usually of the same type, as I said. Understand? So you can't have different models in one particular ensemble technique or algorithm. So it has to be of one single model, right? Or algorithm, basically. So after you've trained it, understand, you've sampled randomly, you've trained multiple models on the different samples. What next? Aggregation. This is basically where the bagging comes from. The bagging here, B stands for bootstrap, Agging stands for aggregation. So for aggregation, it's basically what I discussed earlier: max voting, averaging, and weighted average. So for regression, right, the final prediction is the average of all individual models. While for classification, the final prediction is determined by majority votes among individual model prediction. So this is just the concept of bagging. Like, you need to know this. Like, you need to know this. Why use bagging? Now, I'm going to, as I said last week, we're going to look at what we call overfitting in tomorrow's class. So we're going to look at overfitting and underfitting and hyperparameter tuning and some concepts that you need to know. So we're going to look at some of those things tomorrow, right? But just understand that overfitting in machine learning is not a good thing. Understand? Overfitting is not a good thing. So whenever our model is overfitting our data, we need to stop it. You understand? So now bagging actually reduces overfitting. So training multiple models on different samples helps the overall model not to get too attached to specific. So we're going to look at this thing tomorrow. I can't really wait to explain this so you understand this particular portion. Now, the next one is it improves accuracy, obviously, right? This one is a no-brainer. You know, like two heads is better than one, basically. So, and it also increases robustness. So the final model is less affected by. So these are just the tiny things that bagging brings in as advantage or benefit. Right? So basically, bagging is a powerful technique to make machine learning models more accurate and robust. Right? So by using multiple models and averaging the results, bagging helps prevent overfitting and helps make predictions more reliable. So this is just the conclusion. So before I move on, hope everyone can still hear me and we are still following. Hope everyone can still hear me. Are we still good? Are we still following? All right, great, perfect. So we're going to move on. We don't have time, although we're going to be overshooting today too. So this last stretch of the program, we might be overshooting time, and so yeah. So this is just a diagram that will explain you a sense of what bagging is doing. I forgot to talk about a particular concept. So, but you see here, you can see that this gives you a visual understanding or representation of what is happening during bagging. So step one, what creates n subset from original data set. So in this case, you created 1, 2, 3, 4. You created 4 subsets of data from your original data. You understand? And step two, what you train each weak model with an independent subset in parallel. So for each data set you created, you train it on a model. The second one, you train it on a model. Third one, you train. So basically, after you've done that, you're not going to, depending on the task, you're not going to average it or get the one with the highest vote. So that is going to be your final prediction. So this is just the flow of process or operation in bagging. Understand? So this is it's very straightforward, very straightforward. So the next thing we're going to look at is an algorithm that uses the bagging technique. Remember, I told you bagging is not an algorithm; that it's a technique, and we have algorithm that can use that technique. So random forest algorithm is a bagging technique. It uses bagging in its own algorithm. So random forest is a very popular algorithm. Actually, you might probably have heard about it, right? So random forest is a bagging technique that uses decision tree as its estimator. Remember, I told you that in this ensemble technique, you can actually use some of them you can actually use different models, right? But that model you have to use only that model to train all your data sets, right? So in this particular algorithm, it uses decision tree as its own estimator. Understand? So estimator, now don't let it confuse you. Estimator is the same thing as as algorithm. You understand? But in the context of ensemble learning. So random forest, now it makes actually sense. This is actually a very great notation or name for this algorithm because decision tree is a tree, is a single tree, a mango tree. You understand? That mango tree is can be used to make prediction. Understand? Which can be good or not, which can be depending on how you train it. Random forest now is what? A forest, a collection of trees. So you have plenty trees, you understand? You have like 50 trees. You understand? So it takes many trees to make a forest, as we all know. So that is why we call it random forest. So the random in this name here actually denotes the fact that there is there is a random selection of data from the original data. And also another thing, features too are selected randomly. Remember, I told you that in the bagging technique, you use or you select different subset or you get different subset of your data, right? And you train different models on it. But in random forest selects, you definitely get subsets of your data, right? In addition to that, it also doesn't use all your features. Let's say you have like 10 features in your data set. Now, in random forest, for the first subset, for the first subset, you understand, you are going to probably randomly just take three or four. It's going to take three or four random features, right, and use it to train one model. In the next subset, it's going to take randomly select let's say three or four features. It will be different from the number of features. So the same way you are using different data to train your model, you're also using different features to train your model. So to create your different subsets. So when you train your model on your decision tree on these different features, it's actually going to be more robust and it's going to be more efficient and capture enough relationship. You understand? So there are a lot of things happening under the hood in random forest. So there's a lot of randomness going on. They just know that. So the name actually explains what it does. Random features and random sampling. Understand? And also the forest mean selection of several decision trees or using plenty decision trees. Understand? So let's just quickly go over it. So you can see a random forest is a powerful ensemble and that builds multiple decision trees and merge them together to get a more accurate and stable prediction. So remember we did decision tree the other time, right? And we used to make decision prediction. So in this case, we're using multiple decision trees now to make one prediction. So as you can see, it's a type of bagging technique, but but with an added twist. You understand exactly what I just explained. It not only takes bootstrap samples, but also uses a random subset of features, right? It doesn't, I remember told you about bootstrap sample. Now, in addition to this bootstrap sample, random forest also uses random selection of features for building each tree. So this additional randomness helps to reduce the variance and prevent overfitting. We have said overfitting again for the second time. You understand now that overfitting is a bad thing. You understand? So making it one of the most popular and effective machine learning. So this is a very good algorithm. Like actually, it's a very, very good algorithm. People use it. So we are going to be looking at that, right? So these are the key features of random forest. So it has multiple decision trees. You understand? It has a bootstrap aggregation, which is bagging. You understand? It also has random feature selection. This is actually unique to random forest, right? So high accuracy and handles overfitting. So these are just some things about random forest. So these are the steps in building a random forest. First of all, you select random samples, then you build your decision trees, and then you same process with bagging. So, but you won't actually do this manually. Once you call the class, there's a class random forest classifier. Once you call it to do all these things for you under the hood. So this is just for you to understand what is happening when you are doing all those things. This is the code implementation with scikit-learn, right? So I'm going to let's quickly just demonstrate. We've been talking. Let's demonstrate and see how we can use that in sklearn, or we can use sklearn to implement it. Right. So I believe everybody now is comfortable with using Jupyter Notebook. At this point, feel free to call yourself a data scientist. You understand? In your bio, whatever it is, social media, you're a data scientist. You already have an understanding of all these things, and you can actually work with things like data using ML, and you have intuition on how to approach data, working with data basically. So you can actually start calling yourself a data scientist. Yeah, you can. And I told you before that before we finish this program, you will leave this place, if not with nothing, with the skill. As long as you've committed yourself, you will definitely be confident in your ability. So, but that's just let's just continue with the class. So first things first, you have to import all your okay, let me create this thing inside here. All right. Okay, so we import pandas as PD, import matplot sleep dot pyplot as plot. Now we introduce another beast to that is seaborn. So you can use seaborn sometimes. You can use matplotlib. So depending on the one that is better suited for what you are doing. So now I want to import random forest. I want to use random forest, right? So that's the first algorithm we are looking at today. So what we just basically import it from sklearn and say from sklearn dot ensemble import random forest classifier. I hope that's spelled correctly. Hmm. Okay, so we have it installed already, the same way we installed the other ones, right? So to use it is still the same way we use it using random forest. So if you can just do your tab, you're going to see some of the parameters of random forest and an explanation of random forest. So you can see here that a random forest is a meta estimator that fits a number of decision tree classifiers on various sub-samples of the data set and uses averaging to improve the predictive accuracy and control overfitting. So these are, yeah, I would actually advise you to always read all these things, right? To gain, this is directly from the people that created it. Understand? Directly from people that created it. So it will even give you an idea into the parameters. Remember, I've showed you this before. So first, the most important parameter here is n estimator. Understand? So n estimator mean number of estimators. And what did I say an estimator is again? I need feedback. I need a response. What do I say an estimator is again in context of ensemble learning? What did I say an estimator is? Exactly. It's an algorithm. An estimator in this case is an algorithm. So it can be any algorithm. It can be decision tree algorithm. It can be logistic regression. It can be KNN. It can be SVC, right? So that is what an estimator is. So when you see this particular parameter, n estimator here mean number of that algorithm. So if my n estimator is 1,000, that means I'll be using 1,000 decision trees for this random forest, because random forest uses decision tree as its estimator. So I'm using 1,000 decision trees to train my ensemble model. That is my random forest. So my forest to be very, very, very big. It will have 1,000 trees in it. Understand? So we have other this thing here. Basically, you might not even touch any of them. So, but it's good to always play around with it. So just look at that. So you come and just create your model and say model. You can see RF random forest model, and come and say just copy this here, and then you put n estimator. If you don't put any n estimator, it will be by default 1,000. I'll be 100. So let me put 500, right? So I'm using 500 decision trees. So what I'm doing now is I'm basically training. It's just like you training a decision tree model one time. You go train it again, second time, go train it again, third time. It's like training it 500 times. That is basically what this means. Understand? So this is an ensemble technique. You are using a lot of models, right, to make a prediction, or to you are building a model. You are building a model by using plenty models or plenty estimators. So you have explained that there is no need to go back there. So another important parameter to use is what you already know. It's called random what states. And I need you to answer this question. Why are we using random states in this model, in creating this object? Why are we using random states? I need us to be thinking. We need to always think creatively. Like sometimes we might meet, or we might come in contact with something that we have not seen before. So we have to know why we are doing that particular thing. So why are we using random states now in this particular? Because since we've been creating models, we never use random states. Exactly, for sampling, right? I told you that there's a randomness that goes into the sampling. So if we use random state, it's going to actually capture the exact way it sampled it, so you can replicate it. But if you don't use random state, if you do it the first time, it's do it randomly. If you do it again, it's do it randomly, and like that, and like that, and like that. Do you understand? So these are the things, these are the small things you need to be paying attention to, and you need to be knowing, right? As a data scientist. So you do this, and you've created a model. So you can always come here, things. Okay. Let me see if there's. Because we've created our model, right? So if you run it, you're going to see that we have our model here, and we've put the parameters and estimators and random states 34. So now let's load our data. Let's load our data. So we are going to be using the sklearn data set from sklearn data set import low diabetes. So come and say data equals to data load diabetes, and come and say use as frame, right, equal to true. So I can just come here and say x equals to data dot data y equals to data dot target. So basically, if I say data dot head, oh no, x dot head, you see this here. So basically, this is the data, this is the features are the features I'll be working with. So just display that, but I just move on. So split our data, right? Splitting our data. Come and say x train s test, y train y test, and then so train test split. Then you put your x here and your y and say test size, say 0.02, and say random random state equal to, let's say 20, let's say 34, let's use the same thing and put that there. Come here and import from sklearn.model selection, import train test split. Right, so I'll come and put this here. Okay, so we've done that. You can just go straight to using it to build a model. So I will come and say dot fit and put s train and put y train. So you can see that we are training our model now, and it's actually taking time. You can see that it took time to run. Normally, the previous model we've been doing, like in 2 seconds, it has trained. It's because of what we have here. I told you that we are training 500 decision trees. Let me change it to 1,000. So it's going to take a long time to train. So it will take a longer time, right? See that it's loading here. It's still training. So what is doing now is training. It is going through all this one. The first thing it to do is that it will take this our S train data set now, this S train and Y train, and it's going to create bootstrap samples out of them. So it's going to create that is 500 bootstrap samples, right? And then now train a model on each of those bootstrap samples and randomly selected features, right? So the things that I told you about when I was explaining it is exactly what's happening inside this fit method. So you can just come here and let me import from sklearn.metrics, import accuracy score and confusion matrix and classification report. So import that, and then we can just come here and say y pred. I will say rf model dot predicts our test, say x test, right? Then you say I don't need to run that, just write everything. Now come and say accuracy score is equal to y test y pred, right? So can just say print accuracy so can just do the same thing, just multiply it by 100 and put at the back. All right, so you have this. Why am I getting this here first? I'm not sure how. This accurate. If this is the accuracy score, then it is so bad. Like it is so bad. Well, I don't think. Let me check something. So let me reduce this thing. It's not about round. Okay. So, but this is not the focus for this. So I just want to show us how to use random forest classifier. Basically, it's the same way we've been building our model before, right? So this particular data set. Let me try another data set. So let me use another data set to be sure that it's not from here. So I'll just say df equals to pd.read CSV and say diabetes.csv. All right, so I'm going to quickly do df.column. So I'm just going to quickly go over it because of time. I'm just trying to set it up so I can use it to train the model. So columns dot string dot lower. Come and say x equals to df dot drop dot outcome, and say axis equals to true, and say y equals to df outcome. Right. So I'm not putting comment. I just want to quickly write splitting. Come and use the same thing here. Then do this one. So let me get here and train it. All right. Yeah, so I think it's the data. Oh. I think I know what the issue is. Let me see why. Oh, so you can see from what I just did now, what was the issue? Like, why was that giving me that kind of accuracy score? Like, can someone tell me? So this is basically how you work. This is how you do stuff. You understand? So what was the reason we had that very low accuracy score the other time? From based on what I just did now. Like I don't want to give you any hints, because if I give you the hint, I've given you the answer already. So from what I did, what was the issue? You can see now that I just connect the dots and tell me. I would really like someone to tell me about that. So you need to think like a data scientist. You need to be able to. Okay, so because of time, let me just someone is typing. Let me just wait for 5 seconds, because I really love to hear someone tell me exactly what just went wrong now. Okay, now let me just tell you, this is the Y. I just printed out the Y label. You understand? The Y is what? A continuous value. And I am using what? Random forest classifier, which is a classification algorithm on a data set that is not binary. Like, do you understand? Can you see the reason why we can't use logistic regression or any classification regression for labels that are not binary? Or you understand? So that is just why we had that accuracy the other time. That is why we had the very very low accuracy, and it's even if there's no way you can have that kind of accuracy. So it was not able to fit the data perfectly. So these are just the things that you would see, and it will help you to understand better how this algorithm works. So an oversight. This low diabetes is not for classification problem. So I was thinking the labels are actually ones and zeros. So we just have to keep that one, right? But we can actually use it for classification regression algorithm. So we have random forest regressor. So we can use that for you can use the data set for that one, but we're just going to be focusing on that. So you can see now we've trained on another data set that is the diabetes data set I gave us, and you can see the accuracy is 78%. So if I come here and multiply it by 100, right, and put the percentage here and round it, right, around it to how was the problem? Okay, I think I didn't put my syntax for so accuracy. Let me run this one. All right, so this is what we have here. So basically, this is just how you use your random classifier, random forest for classifying. So these are the things you need to know. You need to know parameters. So these parameters are the things that we're going to be looking at tomorrow. We might not even cover everything, but I'm just going to give you a start on how to do that. So let's just move on because of time, although we would actually overshoot a lot today. So let's all exercise patience. We've looked at random forests, right? And we'll be looking at, so this is basically a diagram illustrating what happens when you use random forest. So you can see each of the model here is a decision tree. You have one decision tree model, you have two decision tree model, and you have the third decision tree model here. So when they give their output or their prediction, it will just come in here, and the one with the majority voting would be assigned as the final prediction. So this is just how it works basically. So this is a very small ensemble decision random forest using just three estimators at this point. So let's just move on. Right, let's just move on because of time. We've looked at bagging. Now we're going to be looking at boosting. Boosting. Remember I said at the beginning that bagging is almost the same thing as this parallel ensemble method that we talked about, where you train each estimator or algorithm individually. Why sequential or boosting in this case uses the sequential method? So the sequential method now, remember I told you that the models that you're training, they are all connected, right? So the first model will be trained, right, sequentially. And then when it is trained, it will have an error basically. So the model that will be trained after it will look at those errors, right? And now improve on it. So subsequently, you'll be getting an increment in performance as you are training more models. So once you've trained like all the models you want to train, let's say you want to train like 10 models, you will now collect the predictions of all the models and use the same techniques, max voting or averaging, to get the final prediction, right? So let's just quickly go over it. So boosting is an ensemble learning technique that aims to create a strong classifier from a number of weak classifiers. You understand? So unlike bagging techniques, random forest, which create independent models and combine their results, boosting techniques trains models sequentially. You need to know this. Like, you really need to know this. You need to know the difference between bagging and boosting. You understand? So it trains it sequentially, while the bagging technique trains it independently. There's no connection. So each model attempts to correct the errors made by the previous models, right? So the primary idea, as I've said a number of times, is that boosting focus on the mistakes made by previous models, thereby improving the overall model performance. So based on this now, you should know that boosting will be generally better than bagging, right? Because you are improving in each model. The next model that is coming is better than the former model. Unlike bagging, you don't know one is better than this one, but you just know that you are training all of them on bootstrap samples. So there's a possibility that this one will be better, this one will not be so better, you get. But in boosting, the one that will be the worst model is the first model. So any model that is subsequent models are actually going to be better performing than their previous model. So that's just the idea behind boosting. So the key features of boosting: sequential learning, right? As I've said different times, weight adjustment, right? So in this case, this is basically how it actually improves or looks at the error that the previous model made. So the misclassified instances are given more weight in subsequent models. So to focus on, so this is how it actually learns and improve on the mistake. So it looks at the mistakes that the model previously made, and it now gives weight, which is a number, to those mistakes, right? To those cases, right? So that it is going to improve and make it basically capture a better relationship. So now the next key feature here is model combination, right? So after you created several models sequentially, predictions from all models are then combined. The same concept that we've talked about, right? So this is just the same thing. So they're not really so complex, you understand? So machine learning is very interesting. So I believe you all have been enjoying this class so far. But so let's just move on. So we have types of boosting algorithms. The same way I said, bagging is not an algorithm but a technique. So boosting is not an algorithm but a technique. Understand? So we have different types of boosting algorithms. We have adaptive boosting, ADA boost. It's called ADA boost, right? So we have gradient boosting, right? We have SG boosting. It's called extreme gradient boosting. So basically, these are the three ones that you most likely be interacting with. We also have light GBM with light graded boosting machine. We have cat boost, categorical boosting. So, but we are going to be looking at these three: ADA boost, gradient boost, and SG boost. So, ADA boosts, like I've explained the concept of boosting already. Understand? So basically, so other boost. Yeah, so basically they use the same concept. So other boost is actually one of the earliest and most straightforward boosting algorithms. Understand? So it adjusts the weight of misclassified samples, giving them more importance in subsequent models. It uses the boosting technique. Understand? So gradient boosting is actually a bit more complex. All right. So it uses what we call gradient descent. We are going to shoot. Gradient descent is actually an optimization algorithm that is used in almost most algorithms that that we know uses gradient descent. So we haven't actually looked at it yet. Understand? But let's just see. Before we round up this program, we're going to talk about it. But it's just a mathematical concept. So that's why I've just been leaving it so that when we've gotten comfortable with all these things and be able to use machine learning models and everything, then we can look at it. So gradient boosting uses that, right? So it builds models sequentially where each new model so the same thing, you understand, boosting technique. So it uses gradient descent to minimize the loss function, which can be so these are just technical stuff. So just understand what boosting is so you can apply it to all these ones here. So, but each of them have their own unique features, right? So, for example, now other boost, you can use any type of estimator. You understand? You can use any kind of estimator in other boost. So, but for gradient boost, I think you're limited to just using decision trees. You understand? Just like random forest. Why SG boost 2 is the same thing. So, but XGBoost is the best out of all of them. I remember I said it before. XGBoost is like the best model you can ever use. So most of these ML competitions that you see that they do online, so XGBoost gives the best accuracy score most of the time. You when using XGBoost, you don't even need to um, worry about missing value, right? XGBoost treats it treats missing value. It takes it into account when building the model. So you don't even need to fill missing value or do anything you get so of that sort. So it's very good. A lot of things that XGBoost do very well. So I'm just going to be looking at let's just finish with this. So we have other boosting techniques. We have light GBM. So you can look up these ones yourself, and cat boost, that is categorical boosting. So now how do boosting work? So we've said this thing, but we're just going to go through the steps. So the first thing is basically initialize weight. So now I believe this is the first time I don't know, okay, I think we've talked about weights before, but weight is just like a value that is used to give importance to certain features in our data. You understand? It's a value basically that we give to different features in our data. But if you give this feature a high value, that means you're giving it a high weight. That means it is important. You understand? So that is what weight means in machine learning. So what machine learning algorithms or model learns in the technical sense is actually weight. You understand? So, but let's not get into that. So, but in boosting, the first thing that happens is that it initializes weights. So it gives equal weights to all the training samples, and then it trains weak learner. So a weak learner now in Ensemble, there are a lot of, see, if I were you, I would have, anytime I pause to explain a particular concept, or anytime you meet a concept that is new that you've not heard before, I would write it down. I'll write it down. I'll write it down. So because this is how you actually get better with data science, because there are so many technical concepts, and if you don't know them, you'd be mostly confused and lost. So all these things I've been saying, it's better you are writing them down. If you're not even taking notes, generally, be writing all this concept down. So after the class, you can just go and look them up, read them up, try to understand what they are even more better. Understand? So because we might not have all the time in the world to explain everything. So weak learner in this case now is actually your estimator, is your single estimator. So is that they call it weak learner because in comparison with the ensemble algorithm, is actually weak. You understand? So after it trains your weak learner, you understand, it now evaluates the performance. So boosting, it is different from bagging in the sense that bagging trains your model, your weak learner on your data set, on your bootstrap sample, and then it just uses the output like that. It just uses the predictions to make your decision. But in boosting, you don't stop there. Once you've trained your algorithm, your model for each of the sample, you then evaluate the performance of all the models. Let's say you train 50 models, you evaluate the performance of the model or the algorithm that is for boosting now. It will evaluate the performance of all the models. When it sees all the performance, then based on how well the different models are performing, it will now give them weights. Remember, it initialized one weight before, it gave all of them weight, but then it will now update the weights. So it will increase the weight of misclassified samples to emphasize the importance in the measurement. So basically, um, this is just how boosting works. So those ones that were misclassified, to pay more attention to it in the next model, right? It's going to give it a high weight value. So when the next model wants to be trained, it is going to like pay attention. So we don't want to go into the detail of all this, right? So but just understand the concept of boosting, and you can see the same way you understand bagging and apply it to random forest. Just a random forest has its own peculiarity. Understand that the same way all these other algorithms have their own peculiarities too. So this is basically the steps. So you train your first model actually, not everything. You train weak learner, evaluate the performance, know where it is not performing well, then give weight. Understand? Um, give weight to those ones that are not performing well. That is the training data, and then update the weight, yes, to the particular training data that is not performing well. And then the next week learner or the next estimator you'll be using is now going to focus on the error or where the previous model didn't perform well, right? So after you have done that, you've done that for all your model, you can now combine everything, right, into a strong learner. So there are two concepts now that we introduce: weak learner and strong learner. Basically, weak learner is like a single estimator or a single algorithm in an ensemble technique. While strong learner is a combination of all your models, basically. So that's just the idea behind that. So you can combine them either by weighted voting or by averaging. So these are the advantages of boosting. It's improved accuracy, obviously, because you are improving on each iteration. It's flexible, right? So boosting can be used with various base learners. So as I told you, other boosts can be used with different estimators of learners, base learners, right? So it also reduces bias. So bias is something we're going to look at tomorrow. We're going to look at variance and bias, overfitting and underfitting, and some other things, right? So these are what boosting the advantages. Now, it also it actually has disadvantages, and the most obvious one is it's actually computationally intensive. Understand? Parallel training is easy, you understand, but training sequentially is very, very, very intensive, you understand, so, and it can be time consuming. So, and also overfitting, it is actually prone to overfitting actually, because it is improving, it is learning so much or in your data. So in this case now, you are actually not getting bootstrap samples. You understand? You're not getting bootstrap sample. You're training it on the same sample, but it's just that you are improving as you are moving forward. So that is actually a difference between this and bagging. So we're going to look at how we can implement some of the algorithms in sklearn, right? So we're going to look at how we can implement that. So we're going to go straight to sklearn, our notebook. Where is that? So we're going to import our classifiers. So I've been using classification algorithms since you can on your own practice with regression algorithms. So it's basically the same step, understand? So it's just that classification tags are actually more common than regression tags. On your own, you can just practice them. So I'll come here and say ensemble and import other boost classifier and also gradient no gradient boosting classifier. All right, so just come and instantiate the objects as simple as that. And come and say using other boosts. I'll say other model. And come and say other boosts classifier. So basically, you can just do your shift tab and look at the parameters. Now you have estimator, right? You have n estimator, you have learning rate, you have some other things here. So now estimator is actually the algorithm you would want to use. Understand? So in this case, let's say I want to use logistic regression first. Understand? I'll just come and say my estimator, or let's say let me just say estimator equal to logistic regression. So you have to import logistic regression. right? So just come and say sklearn dot linear model and import logistic regression. So we come here and then say estimator equal to estimator. Let me just change it to log reg, right? I come and say log reg. I can actually use I can use SVC, right? I can come and say SVC. Come here, I can use any estimator I want to use. I just have to import them. So in this case, I'm using this one. Let me comment this one out. I'm using this, right? So another parameter we have is n estimator. So number of logistic regression models I want to use. N estimator. So by default, it is what? Let's check again. By default, it is 50, right? So let's just make it 20. Understand? Or let's make it 100, right? So we've basically built our other boost classifier. We can now train it on our data. We can come and say other model dot fit. You can also S train and Y train, and you come and say, let's just run that version. So basically, it's giving me some warnings that maximum number of iteration has reached. So I'll just have to increase my max iter. Come and say max iter equals 1000. So come here and train it. So what is saying? Same are duplicated. This is not an error, this is just a warning. Understand? So that the different level of logs in Python, that one is a different thing on its own. So you've created your other boost. As you can see, the estimator it is using is logistic regression, right? This is other boost classifier, and you're using 100 of logistic regression models, right? So you've trained your model. You can now try using it to make predictions. So you can come and say y pred equals to other model dot fit and predict, right? And you see x test, and you come and say accuracy. And let me just import this print accuracy. So I'm not paying attention to the evaluation. You don't just use accuracy like that. You have to check for your classes to know that the classes are balanced before you use accuracy as an evaluation metric. So I'm just doing it just get a glance of how the model is performing, right? So if I run this, you can see I'm getting 79.9%. So this is the same data using other boost. I'm getting a higher. I'm getting 78 here, not so much, right? Here I'm getting how many estimator 50. So I'm getting how many here? I'm getting 79, but that's almost 80%. So if let's say, let me just change something. Let me change this. Let me the number of estimator at 50. Let me see if it will make any difference. Train this and then make these predictions. So it's still the same thing. Now I can actually change the estimator to a decision tree. If I did not include anything here as estimator, it will by default use decision trees to make the classification. So if I run this and come here and run this, you can see it just give us this thing. So by default it is using decision trees to make the to build the model. Come here, you can see that the accuracy is higher, 80.5, right? So basically this is how you can use other boosts. These are the basics, right? So that's things you can do to tweak it change the hyperparameter. So all these things I'm doing, changing this thing to 100, changing this max theta to 500. So these are actually what hyperparameter tuning in. That's what we're going to do tomorrow. So doing all these things to make sure or to improve the accuracy of your model is hyperparameter tuning. So that's just a glimpse of what we're going to be doing tomorrow. So now this is how you use other boost, like very straightforward. So other boost, you can specify the estimator you want to use. So you have to import it. You can use SVC, spot vector. You can use KNN. You can use a lot of other classifiers, right? So let's just look at gradient boosting classifier quickly. So I'll come here and see grad model and come here, just run it. So I can just put my this thing here. You see the different stuff that we have here. So there are a lot of parameters here, a lot of parameters. So in this one, we don't have estimator, so you can't specify the estimator to use. You use decision tree that it's using, so you can't actually change it. So you just have to work with that. Come and do the other training. So you say grad model dot fit. You say x train, y train, and you run that. If I can spell this correctly, the model will run fine. So come and copy this, and I'm going to change this to grad model. So you can see the accuracy it actually is lower than the other one. So you can just improve it by changing some things in this place. So number estimator is 100 by default, right? Max depth is 3. Let's see if you can change this max depth. Come here and say max depth, let's change it to 5, right? Let's change it to 5. Wow, it actually decreased the accuracy. So the max depth, it's making it overfit. It's actually overfitting it. Let's see. 74%. So let's use 2. Alright, so I think that 5 is just the let's try to use n estimators. Just give me a glimpse of what we're going to be doing tomorrow. So let's use 50. I think the default is 100. So okay. So let's change it to 100, 1000. That's actually going to take time to train. So this is just how you use these things. Like it's straightforward to use, but you need to know what you are doing. You understand? You need to know what you are doing. So we've looked at other boost and gradient boosts, right? You can see this as trend. Okay, so the accuracy basically can't go beyond that for now. So let's just continue and round up what we have for today. So come here and say so you can just play with other things like other data sets using these different algorithms. So this is the chart describing the flow of operation. So as you can see here, you have your complete data set, right? In this case, you are not bootstrapping. You are not creating bootstrap samples. So the step 1 is you assign equal weight. This is the first model that you are creating, right? So once you train it, then you're going to get the accuracy and the error. And the error, the model is going to analyze the error and look at where the error is coming from and assign weights to those particular cases and now use it to train this new model. Remember, the initial model was trained, but it has equal weights. But now the new model had adjusted weights, right? So these weights are the things that will determine how much of how much improvement the subsequent models will have. So you can see this just shows us the flow, and after it has been trained, everything has been trained. So each model now would now make its prediction. So the first one, second one, third one, fourth one. So basically, we're not going to use a criteria to get the final prediction. So this just illustrating exactly. You can, when you get the material, just go through it and look at it, right? So now we're going. This is the last thing we're going to do today. SG boost. So I've told you about SG boost already. So as you can see, it's gradient boosting on steroids, right? SG boost is actually a crazy algorithm. Like it's very very good, like, very good. So most people that do competitions, competitive program data hacker things, they use SG boost to create a machine learning model. So as you can see, it's actually a powerful and efficient implementation of gradient boosting algorithm, and it has become one of the most popular tools in data science competitions and real world applications due to its high performance, speed, and scalability. So we're not going to go deep into SG Boost, right? To just understand that it's very fast. And one thing that makes this boosting to be slow is the sequential method, right? So it takes time to do that training, but SG Boost actually trains in parallel. Yeah, yeah. So SG Boost actually process. So as you can see, it supports parallel processing, which makes it faster. So that is what makes it faster actually. So so we are going to just go over that, and parallel processing, and you can see here handling missing values. So SG can actually SGBoost can automatically learn how to handle missing values. So you don't need to do simple imputer or do fill any or this one or that one. You get SGBoost, just take scale your data and put it into, you don't even need to scale your data, right? Most of the time, because decision tree, they they are not prone, like they can work well with unscaled data. So these are the things that you would need to know, like which model would work best with scale data. There's some model self that you need to use a particular scaling technique. You need to use standard scaler for that particular model to be very efficient. Some you need to use min mass scaler. So these are the things that you need to be doing, or that you are going to be doing as a data scientist. You are going to actually be working as a scientist, testing this one if it's going to work. Do you get an hypothesis, test it on this one, check the output, test again and everything. So you're just going to be going to and fro. It's going to be an iterative process, you understand? So yeah, that is just it for that. So we're not going to go into the other ones. So this regularization, we are going to be looking at it tomorrow, right? So all these things you can just look at them. So these are the things that that actually make SG Boost a very good algorithm. Understand? So the handling missing data and parallel processing, they're just the two key features that you need to know about SGB. So the advantage is fast, yeah, very fast, has high accuracy, flexible, and is also scalable in the sense that it can be used for both small and large data sets. Understand? So and it supports distributed computing. These are just advanced ways of doing machine learning. So now the last thing we're going to do is just to show us how we can implement SG Boost. So SG Boost is not, you cannot implement it with sklearn. You need to know that you can't implement SG Boost with sklearn. It has its own different library. You understand? So to use SG Boost, you just have to I think an account that doesn't have SG Boost as default. So let's say SG Boost as SGB. Okay. I've installed it. I've installed it on my computer. But in case you try installing it and try importing it and it doesn't import, this is what you should do, right? So let me just come here. So in case you try installing it, so I don't want my DM to be filled with messages. So I'm saying it now. In case you try installing SGBoost and it doesn't install, what you should do pip. Before you do pip, you write a question, an exclamation mark, and say pip install SG Boost. You run it. You need to be connected to the internet to do this one because it's downloading it from Python repository, right? It's installing from Python website. So you need to be connected to the internet to be able to install this. So once you don't have SGBoost on your system, this is what you should do. You install it using pip. Pip is a Python package manager. The reason why we've not been using pip is because we are using Anaconda, and Anaconda has most of the packages we have been using so far. So in this case, the SGBoost might not be in Anaconda. You have to use pip to install it. So before you use the pip, you have to use your exclamation mark, right? So because basically we are not in the command line or terminal, so we need to use this magic command to basically this is just the command to use. So let's not just so the reason why it's showing me this is because I already have it installed in my computer, so it didn't install anything. If you didn't have it installed, it will show you a lot of messages downloading this and the rest. So basically is what you should do. So once you've done that, you import it SG Boost. So you can see it here, right? So extreme gradient boosting library and everything. So this is just the summary. And or you can come here and say from SG Boost, from SG Boost, import SGB classifier. So this is the classifier we're going to be using. So this one is different from sklearn. You are not importing it from sklearn. Note this, please. So you run that, and then you can now, but the same way you use sklearn.fit is the same way you still use SGB. So you can come and say SGB model. You can come and just say SGB classifier, right? And then you can train it on your model, on your data rather, and say SGB model.fit and say X train, Y train, right? So you can see it's giving us a different outputs. So a lot of stuff here. These are the parameters that we have here. So we didn't include anything, so most of them are none. So you can just make the prediction. Let's just copy this one that we have here. I'll come and say SGB. Right. So we see it's having 72.1%. So we just have to do a lot of hyperparameter tuning to actually get the best out of it. But yeah, this is how you use it. You understand? So we actually introduce a new way of installing a package, right? So just take note of this in case you have issue with importing SG Boost. So that's going to be it for today's class, right? That's going to be for today's class. We introduced ensemble technique. Right. So I actually planned on doing PCA. PCA is a feature engineering technique, right? I was like, if we had enough time, I'll just quickly go over PCA. But since we don't have enough time again, we're just going to leave that till next time. But basically, what we had for today, we are done. We have looked at ensemble technique from start to finish. So now you can comfortably I use this in sklearn, and I believe we have an understanding too of what ensemble learning is and the different methods: bagging, boosting, random forest, SG boost, other boosts, gradient boost, that, and everything, sequential, parallel, bootstrap sample. So there are a lot of concepts to introduce in this class. So please just go over this video again and pick up those new concepts and learn them very well. Understand? So we're going to be calling it a day here. And but before we do that, I'm going to be giving rooms for question. Right. So you can now ask your question. The floor is open. So if you have a question, just indicate by raising your hand, and I will unmute you. Any question? Anybody? Do we all understand everything that has been taught today? All right, Timothy. Yeah, you can unmute yourself and speak, Timothy. Mr. Timothy,
Okay, thank you. Thank you very much for today's training, sir. I want to ask, you talked about the estimator that other boosts can use. You talk about that of gradient boost.
we can't
What
hear
of
you.
that
I don't know if
of...
you're speaking, but we can't hear you. I can't hear you.
Hello, can you hear me, sir? Hello, sir, can you hear me? Oh, good. Network.
Okay.
Sorry, please,
Try
can you hear me?
refreshing your network or something, because I can't seem to hear anything you're saying.
I can hear you.
I
I can
think
hear
it's
you.
from my end. Yeah, please go on again. I actually just, it was my fault. I disabled the
All right,
speaker. So, yeah, you can ask your
all
question
right, sir.
again. So,
All right, thanks for the class, sir. You talk about the estimator that other boosts can take. You talk about that of gradient boost. What of the SGB boost? What are the what is it just decision tree that SGB boost can also take, or any
yeah,
other
yeah, yeah.
algorithms?
I thought Edge boost is extreme gradient boosting. So, the same concept in gradient boosting. It's just that some tweaks were made to gradient boosting with like parallel processing, right? And some other things that makes it faster and better. Thing is that we don't really have that time to go into the anatomy of these algorithms. Hence, we won't actually achieve anything in a day. So, just giving you an overview of them, give you an understanding of what boosting is. So all of these boosting algorithms, they rely on the boosting technique. So if you understand the boosting technique, you understand like 70% of what all these algorithms, how they work. So if you want to know how they work, don't worry, just meet me. I can give you resources. You don't even need to meet me because the textbook that I sent will give you a breakdown, detailed breakdown. YouTube videos, I'm going to send it to us during the week to help us understand better all these algorithms, right? So the concept is still the same thing with the other ones we've mentioned. So um, yeah, just just keep that at the back of your mind. I understand. Sometimes you might actually want to understand how this thing works, but I really wish we have enough time and would have gone over that, but that is just it for this class. So are you okay with that? Is that the only question you
All right, thank you, sir. I'm okay, sir.
have? Okay. All right. But the can go on to ask your question.
All right. All right. Good evening, sir.
Yeah. Good evening.
Yeah. So thank you for the class. What the question I want to ask is, uh, dealing with a real life project. Like maybe I'm working for a firm and they gave me a project to work on. Like, I understand that there are some things that we need to do during data cleaning and pre-processing. Like you check for missing values and the duplicate values. But I noticed that we've not been. I don't know. Maybe it doesn't affect our data that much. Outlier. I want to know. Uh, is it compulsory that every time before we start to go ahead to train our data, should we remove the outlier or do you understand what I'm trying to say? Whether we need to
Yeah.
remove it or we need to do something.
Yeah.
So
I
do we need
understand.
to all
Yeah. I understand your question. So yeah, during data cleaning, we talked about handling outlier, and I believe there was an assignment where I told us to remove an outlier basically. So see the thing about working with data is that you can't really capture every single thing, every single approach. Understand? So your data is actually going to be what would inform your choice or the decision you make during cleaning. Understand? So that's why I said as data scientists, we are basically experimenting. You're always experimenting. Your data would be talking to you and you would be working based on what you're saying, right? So, but the thing is that outliers generally they are not good for ML. Generally, they're not good, but there are some models, or most ML models have been built to be robust to outliers. So whether you have outliers in your data or not, it's not really affect your model, but not all of them. Understand? So that should I'm giving this as a research question back to you to go and to go and list out or to know all the algorithms that are robust to outliers and the ones that are not really robust to outliers in the sense that outliers would affect them. Understand when you are using them. So just go back and read up and check the characteristics of these algorithms in respect to outliers. So outliers generally is not good, right? So it's telling you, although sometimes it tells you something about your data, it might be a wrong input, sometimes it may actually be a valid input, right? It might be a valid input. So these are just some of the questions that you'll be asking yourself when working with your data, right? So yeah, that is it for that. That is it. So you just have to do more research and just work, practice more. The more you practice, the more you gain intuition and the more you know how to work with data. You cannot unless you work with data, you clean data a lot. You cannot know how to do all these things. Whether no matter how many theory you know in your head, how many concepts, if you have not done it before, if you've not handled missing values, outliers, done all these things like practically, there's a kind of knowledge that comes from doing
Yeah.
practical stuff, like especially data science. There's a knowledge that comes that can't be explained. You just feel it. You just know that this is what you're
Yes, that's
supposed
true.
to do. You understand? So I can't really capture all these things with in a word or something. So just that's why I keep advising us to keep practicing and keep learning. You understand? So I believe that that is enough to answer the question.
Thank you, sir.
All right. So we are going to be calling it. Do anybody have any other question before we call it a day? All right, Adimo, you can speak now. I'll unmute you.
Yes, can you
Yeah, I
hear
can
me?
hear you. Yes, sir.
Actually, today class is different. It's a new concept actually, but we are able to gain a lot. My question is that you've been talking about um reproducibility a lot of times. Can you schedule a day for us that will take us through that process?
What process? Process?
How to reproduce our
What do
works.
you mean,
Like
sir?
if I perform to reproduce our models. Like by
Is it
you always talk
is it
about
a random
the
state?
random state and a lot of and you made mention of it a day. I could remember that you take us through the process of reproduce our work. So I think I can remember that.
Yeah. There's actually nothing special about reproducing your work. It's just including the random state parameter in your class or your function. So once you indicate a number there, understand, and you run that model,
Okay.
reproducibility in this sense is that when you do it again, it is still going to use the same sample. or the same random sample that it's used before to create your model. That is just what reproducibility mean in that sense. You understand? But if you don't include random states, the model will
Okay,
randomly select samples each time you are doing it to
okay,
do it differently. So it is not actually reproducible. You're actually not using the same set of data. Like, you understand what I'm saying? So that's just what it is. So it is not really a special
okay,
concept that needs a dedicated time for.
oh, okay,
Yeah.
okay, okay.
All
Thank
right.
you, sir.
All right. So
All
I'll
right.
take the last question from about Nego. Yeah, please go on to speak, sir. Hello, sir. Can you hear me?
Good evening, sir.
Yeah, good evening, sir. I can hear you.
I can you,
Hello.
sir. Good evening, sir.
Yeah, I can hear you, sir. You can go on.
Good evening, sir.
I can hear you, sir. Please go on to ask your question.
Okay, thank you for the opportunity.
Yeah.
Uh, what I want to know, like, hello, can you hear me, sir?
The line is breaking. I can barely
Yeah,
hear
the
what you're
data
saying.
set,
Okay.
like the cleanup of a data set, is it all, all the data set that we are using that we need to check to clean up, or there are some that are already in order that we don't need to clean up? Hello, sir.
Yeah.
Hello,
Um.
sir.
Yeah, I can hear you. Yeah, I
Hello,
can
sir.
hear you. I can hear you.
Can you hear
I've
me,
gotten
sir?
your question, sir. Let me
Okay,
respond.
like the data
Yes, I can hear
sets
you.
that
Yeah, I've
we
gotten your
normally
question.
use, like the past data set that we use, when I checked to clean up, is already in order. So, like other data set that will be using as data scientists, do we also always need to check to know whether they are in order or not before?
Yes, yes,
Do you
yes,
understand?
yes. I
Okay,
understand
okay.
your question.
It's okay, it's okay.
Yeah.
Okay,
So
thank you.
the thing is that
Thank you.
I give you data set based on what I want us to focus on. When we're doing exploratory data
Yes,
analysis
I can hear you.
and the other data,
I can hear you now.
while we're,
I can hear you now.
while we're doing exploratory data analysis and the other data cleaning techniques, I intentionally gave you data set that is not cleaned, so you would practice on how to clean it. But when we now start focusing on building ML algorithms and preprocessing, so the data set I give is specific to the task I want you to do. But in the real world, you actually most likely not even encounter clean data sets. You understand? So with the knowledge you already have in data cleaning, you would now use it. So when you are given a data set as a data scientist, the first thing first, remember the process, the data science life cycle I gave us initially. Data collection, then you have your data cleaning, you understand? You now have your data cleaning, pre-processing, and then you now do your EDA, and then so data cleaning is a step in your data science life cycle. It is a step. You don't miss it. You have to be sure that your data is clean. If it is clean, then you move on. If it's not clean, then you clean it. So that is just always keep that at the back of your mind as a very important step. So I believe that that has answered your question. So we are going to call it a day now. We've actually gone so far. Sorry for the time overshooting. You can actually go back to the class recording and watch it. So please, as usual, drop what you learned today. Let us see what you learned from the class, and just share it with us, and I'll be in the DM in the group waiting to see them. So I'm going to see us tomorrow by God's grace. So try to watch the cloud, try to drop it as soon as I can. So try to watch it and prepare yourself for tomorrow's class. So tomorrow we'll be looking at hyperparameter tuning and overfitting bias variance, right? So we are going to do a lot tomorrow. Tomorrow is going to be very, very, very interesting. I might not finish everything tomorrow, but we'll have a very good foundation tomorrow. So yeah, so from me to you, have a very, very, very wonderful evening and enjoy the rest of your day. Thank you very much.